The mole. So in this video, we're going to discuss what the mole is and how this relates to something called Avogadro's constant. I've posted a YouTube video that explains exactly how big a mole is. So if you haven't watched that yet, I want you to stop it here, go back and watch it, and then come back to this presentation. So what is a mole? As far as chemists are concerned, we kind of think of this as our dozen. So if I were to say to you, what is a dozen of something? If I had a dozen eggs, for example, what does a dozen mean? And you'd probably say, oh, a dozen, that's 12 of something. Or what if I said a pair of socks? What does a pair mean? And you might say, oh, that's two of something. Or how about a ream of something, like a ream of paper? Yeah, I didn't know what that was myself until I looked it up. That's 500 of something. So when we talk about a mole, this is just a particular quantity that chemists use to help us measure amounts. Why is Dwight Schrute here? Send me a message if you know. Okay, so by definition, what a mole is, the chemist doesn't. It's an amount, it's a unit that we use to measure the amount of a substance. And when we say an amount, that can be a lot of different things. So an amount, you could conjure up ideas of maybe it's the mass of something or the volume of something. With a mole, this is a number of particles. By definition, our working definition of the mole, it is equivalent to as many particles, and particles can be atoms, molecules, or what we call formula units, I'm going to get to in a moment. But the number of particles that can be found in exactly 12 grams of the isotope carbon 12. So, what this would be equivalent to, if I had a 12 gram sample of carbon 12, this would be counted as 6.022141179 times 10 to the 23 particles. It's a really, really, really big number. So a mole of something is that equivalent, 6.02 times 10 to the 23 particles. So if I had a mole of copper, I'd have 6.02 times 10 to the 23 atoms of copper. Or if I had a mole of sucrose, I would have 6.02 times 10 to the 23 molecules of sucrose. Or if I had a mole of sodium chloride, that's table salt, that's equivalent to 6.02 times 10 to the 23 formula units. And formula units, this is just what we use to describe ionic compounds. We're not going to call it a molecule of salt because sodium chloride isn't actually a molecule, but a formula unit is the type of particle that we measure ionic compounds in. So when we talk about particles, they can come in one of three varieties. So we could have atoms. I mentioned copper before, but a mole of copper, 6.02 times 10 to the 23 atoms, would be in 1 mole of copper. If I had a mole of gold, 6.02 times 10 to the 23 atoms of gold. For some substances, they don't exist as individual atoms, but rather they exist as molecules, covalently bonded, atoms covalently bonded to form this type of particle. So here we've got an example of water. You can ignore the hydrogen bond for now, but look at the covalent bonds holding your oxygen and hydrogen together. So if I had a mole of water, that means I have 6.02 times 10 to the 23 molecules, an entire H2O unit of water. In formula units, this is what we use to represent or count particles of ionic compounds. Sodium chloride, let's imagine here that I have a nice little sodium ion and a chloride ion. Here's the crystal lattice. And when I had the formula NaCl, that means for every 1 sodium, I have 1 chloride. I'm not going to call it a molecule because it's not covalently bonded. But if I had a formula unit of sodium chloride, that means I have 6.02, a mole of sodium chloride. That means I have 6.02 times 10 to the 23 units of NaCl. So for every 1 sodium and 1 chloride, that would be a single formula unit. A mole of those, 6.02 times 10 to the 23 as much. Now from the video, we kind of were introduced to the work of Avogadro and saw that some other scientists at the time kind of rejected his ideas. But Avogadro's constant, really what it is, it's the number of particles that you find in 1 mole of a substance. So we said that a mole, our working definition, is when you have 12 grams of carbon-12. If I have a mole of maybe something like copper, it's probably not going to be the same mass. It's not going to be 12 grams. Copper atom is a lot larger than a carbon atom. And in fact, if I had a mole of copper, it's about 63.5 grams for 1 mole. But if I have a mole of copper, much like if I have a mole of carbon or a mole of gold, it means that I have 6.02 times 10 to the 23 atoms, or 6.02 times 10 to the 23 particles. So Avogadro's constant, we represent with this notation capital N, and that capital N we're going to see a little bit later, that's a number of particles, but that little subscript capital A helps us denote that it is this constant value. Now, if it's constant, it means that it's unchanging. So Avogadro's constant tells us, regardless of the type of substance we're working with, if you have a mole of it, it's 6.02 times 10 to the 23 particles. So if we have this value, if we know this constant, that can be used to help us find the number of particles in a sample of a substance. So I'm going to give you a quick example here. Let's say if I had 1 mole of copper, that would be 6.02 times 10 to the 23 particles, or 6.02 times 10 to the 23 atoms of copper. Now, instead of having just 1 mole of copper, how many atoms would I have if there were 3 moles? In other words, if there were 3 times as much. So think about it for a second. I know the answer is right below. But if you had 3 times as many, then what we're going to do is just take that value, Avogadro's constant. This tells us how many atoms or how many particles are in 1 mole of copper, and I've just multiplied it by 3. Now, if you take a look at how I've set this up, notice every time I write down a number, I'm always going to write down a unit with this. As I've shown this here, my moles and moles, they would cancel out, and I'd be left with a value that's shown in particles. With this one, I haven't rounded it just yet. We're going to get to that in a moment. So for those of you who know about your significant digits, just hang on. But it's simply showing us that if we know how much we have, how much in moles, this little new unit that we've introduced, we can actually calculate how many particles are present. And again, those particles can be atoms, molecules, or formula units. And here it is again, but this time I've rounded it. So 3 moles, that many particles per mole. And notice here I've rounded my final answer to 1.8 times 10 to the 24. If I was looking at this value, that's 2 significant digits. We don't count the digits that you see in your times 10 or the exponent. So this has been rounded to 2 significant digits. If you go back to the rules that you looked at before on significant digits and scientific notation, where I've decided or how I've determined that it should be 2 digits is by looking back at the values I was given, and we're going to go to the fewest number of each. So this is multiplying and dividing. In that case, we're going to go to the fewest number of digits. So I've got 2 sig digs here. Now this is a constant, so we're actually not going to consider that as part of as significant digits for our final rounding. So I'm going to go to 2 significant digits based on what you've been given in the starting values or the question. Okay, so what I've done here with that first example, we've actually just shown how you can figure out how many particles there are if you know the amount in moles. So we're going to use this formula to help us. And of course, this is chemistry, so why would we make things easy, we're going to use every variable in this formula with the same letter. So we have a capital N, a little n, and then another capital N with the subscript A. I would really strongly suggest and you probably will as we're starting to learn this, if you find this a little bit confusing, given the fact the variables are all the same, one thing you could do is maybe just get a cue card and write down these values and variables and what they represent, just so you have that kind of handy as you're working through some practice problems. So the relationship that we're showing here is you can find n, which is the number of particles, if you know little n, which is what we use to denote or to show the amount of something in moles. And since we know Avogadro's constant, which states that every mole of a substance is 6.02 times 10 to the 23, I can find out how many particles by multiplying those two values together. Okay, similar to what you had just done on our previous example. So if you take a look at the handout that I've given you, I'm going to give you two calculations, just kind of working with actually that same formula, just two different things that we're solving for. And these are both examples of how you can convert a substance from moles into particles or particles into moles. Now, the sample that I've got here, I've got my full solution kind of according to or using my GRASP format. I tend to mark, if you recall, kind of the ASP of GRASP, our first unit, our isotope calculations. You can write down your givens and your requireds, but where I would start marking or looking for a solution would be at this step where we introduce our formula and then substitute in and come up with a therefore statement. So here's a quick example, two quick examples, but this first one of how you can find out the number of particles in a sample of a substance if you know how many moles are present. Again, a mole is just an amount. It's a new way, a new quantity that we've introduced. So as I read through this question, I'm just going to highlight a few key points, and you're going to see with my given and required, I'm just kind of recording as I go what I know and what I need to find. So here's the question. How many molecules of oxygen gas? Oxygen gas, remember, oxygen's a Haber-Finkel, it's O2. So it exists as a molecule. How many molecules of oxygen gas are in a room that has 8.5 times 10 to the power of 3 moles of oxygen gas? So as I read through the first part of this question, how many molecules? Another way that I could think about that is how many particles? And I've just been really specific that the type of particle I have is a molecule. It's not an atom and it's not a formula unit. It's a molecule because O2, oxygen gas, is a covalent substance. So I've written N equals, I don't know, because capital N represents number of particles. The next thing that I'm told is how much gas I have. I didn't give you a volume of gas or a mass of gas. Rather, I've given you this new quantity, how many moles. So I have 8.5 times 10 to the power of 3. And I'm going to put MOL, which is the unit symbol for mole. So you know, like for mass, you'd write G for grams, or for volume, you might write a capital L for liters. For moles, the short form, the unit symbol, you just drop the ES and it's an MOL. So there's our unit symbol. Now, I've only been given one piece of information. However, I do know one other fact, or should I say a constant. I know Avogadro's constant, and it's constant, it's not changing. So we know that 6.02 times 10 to the 23 molecules or particles would be in a mole of a substance. So I'm going to use this constant to help me figure out how many particles in total. So here's my formula. Number of particles, number of molecules I'm trying to solve for is moles times Avogadro's constant. Notice when I've substituted this in, I've written down molecules rather than just leaving it as particles. I've been really specific. Like I know what type of particle I'm trying to find. So be as specific as possible. Okay, I'm going to find how many molecules of oxygen. I'm going to multiply these values together. My final value, I have not rounded it yet in this step. 5.117 times 10 to the 27. That's a lot. And just think conceptually, does this make sense? 1 mole is 6.02 times 10 to the 23. I've got way more than 1 mole. I have 8.5 times 10 to the power 3. That's like 8,500 moles. So this number, this value, yes, it should be much, much bigger than just the number of molecules you find in an individual mole of a substance. Now for my final step, for my therefore statement, notice that I've now rounded this to 2 significant digits. The 2 digits, where do they come from? Why 2? Why not 3? Rule of multiplying or dividing, if that's the only operation that we're using, and we're going to round it to the fewest number of significant digits, basically our least accurate measurement. So if I look here, 8.5, that's 2 sig digs. And here I've got a constant, so I'm not going to actually consider that in my final calculation. So overall, I've converted from an amount in moles, just tried to identify how many actual molecules or particles that is. And that's a bunch, apparently. Okay. Now, the other calculation that I'm going to have you practice is just going the opposite way. So what if you were able to identify the number of particles in a particular sample of a substance? Can you convert that into an amount in moles? So here's our formula, same one that we used, just rearranged from the last example. If I want to find moles of a substance, I'm going to take the number of particles divided by Avogadro's constant. So here's the second example. You have a gold coin. I don't know who's counting, but we find out that there's 9.51 times 10 to the 22 atoms of gold. What amount in moles? And again, amounts can be lots of things, mass, volume, but we're going to look at what is that as a molar amount. What amount in moles of gold is in this coin? Before I even start this, I'm going to look at that into myself. I'm kind of thinking that is less than 6.02 times 10 to the 23. So how many moles is this? It's probably going to be less than 1 because I don't actually have a full mole of gold. So let's read through our question, highlight, and find out what do we know. Okay, we have 9.51 times 10 to the 22 atoms. Okay, what are atoms? They're particles. So I know capital N. That's my number of particles. Notice I've written down atoms, being very purposeful here in identifying the type of particle. What amount in moles do we have in this gold coin? So that's little n is just changing to amount in moles, and I don't know what that is. Na, Avogadro's constant. Notice it's not in the question, but I know this relationship. So as soon as I see this kind of conversion between atoms or particles and moles, then we're going to introduce and use this constant. Notice I haven't written particles per mole. I put atoms because I know specifically what type of particle I'm trying to find. Okay, here's our formula. To convert to amount in moles, let's take the particles divided by Avogadro's constant. And when we plug those in, and if you've done this correctly on your calculator, you will have a value. Yep, that's definitely less than 1. So little n, that's my amount in moles. If you're finding you have any difficulty perhaps getting the correct final answer, let's say you've set everything up properly, but you're finding that you're just not quite getting this value, maybe the decimal is a bit off, just pop onto the Meet and let me know and have your calculator ready, and I can try to do a quick tutorial with you to make sure that you're entering these values in like properly on your calculator. There's a few tricks to it depending on what kind of calculator you have. So here's our amount. I'm going to round my final answer to the correct number of significant digits to help reflect the accuracy of our measurements. And you'll notice here that I've got 1, 2, 3 sig digs and a constant here, so I'm not going to consider it. So I'm going to round my final answer to 3 significant digits. It would also help if I had rounded that properly to the correct number of significant digits. So, 0.158 moles of gold would be in the coin. I'm going to go back and fix that. Nobody's perfect. 0.158 when I've rounded that to the correct number of signigs. I put that in there to make sure you were watching. Okay, so as you go through these examples, what I want you to do is keep in mind significant digits in your final answer. You do not have to round to the final and the final number of signigs until your therefore statement. We're just using multiplication and division rules. And please try to use your steps of grasp. G and the R are optional, but definitely the ASP of grasp. Please make sure you include that with your full solutions. If you have a copy of the note or our handout, you'll notice if you looked at our doc, the second page, not even the second page, that's like the fourth or fifth page, it does have the answers already calculated and put in. I'm going to leave that up to you if you want to. If you have a printer at home, you can print it out and include your own writing on the notes, or you can type into it. You can keep electronic copies, but basically most of our notes are going to follow that format. Okay, so here in front of us, I've got a simple version of, I think, the calculator that at least something like this that I had. And as I said, everybody has different ones. Some people have fancier calculators. But what I wanted to kind of highlight here, there's a few key buttons that we can use when we're trying to enter values into our calculator. So if I wanted to put in a number like 6.02 times 10 to the 23 on this version of the calculator, this is how I would do it. And I'm sorry, like this new program doesn't have like a highlighter function. So just follow my arrow. You find it? Here it is. White arrow on a white background. So if I wanted to type in 6.02 times 10 to the 23, I'd hit 6.02. Okay, you with me? And then instead of trying to hit multiply or using the 10 to the power of button, what you're then going to hit after that 6.02 is EXP. On some calculators, this pops up as an EE, or some others may have kind of like the little arrow and a 10 after it. And then after I hit that, I'm just going to type in 23. Okay, so for example, this one, ignore what's up top. We're doing a bit of calculus. 2.1697 times, you notice here's little times 10 to the negative 1. When you hit that EXP button, what it does, it just instantly puts in that times 10 to. And then after that, you just type in your exponent. So play around with your calculator, especially go through those first two examples. And if you have any trouble getting the same number as I have, presuming they're rounded properly, please just hop on the Meet and I can help you with that. Okay, so that is the end of moles for today. We're going to continue working with them tomorrow. As I said, maybe create kind of like a cue card or something to keep handy as we're just learning what each of these variables represent. Okay, if you have any questions, I will be on the Meet.